This is Steve Waller with Vcinity. Today we're going to talk about how we can exploit RDMA to create a geographically dispersed storage network, and we're going to do that over the WAN. And what it really enables is real-time access to remote data. Now the agenda for the talk is first we're going to talk about the challenge that we needed to solve. We're going to talk about our particular solution, and then I'm going to show you a demonstration because this solution is very different, very unique. I'm going to show you how we accomplish this, and then we're going to talk about what this really means and how it enables a differentiation in the way that you use data over distance. Now, the fundamental problem is right here. It's that data is created everywhere, but is that data created where it really needs to be? Is it near the compute? Is it near the applications? And 9 times out of 10 that it's not. And what ends up happening is that we focus more on moving and copying and replicating that data. And we have to do that multiple times because we have to get that data to be near the compute and the applications. Some of the problems associated with that are pretty straightforward. How long does it take to actually move that data? The faster that it moves, maybe it's the quicker that I can monetize that information. Remember, there's a perishability associated with data. By the time I move it, it might be stale. And is it safe? Is it safe in the transport? What about where it lands? Is it safe there as well? Remember, the more copies I have, the larger my attack vector is for people to try to get to that data. And in some cases, am I even allowed to move the data? Remember, there's compliance and regulations and sovereignty rules. Maybe I'm just not allowed to move that data. So then how do I use it? And this fundamentally happens because of one age-old paradigm. It's been around since computers were created, which is in order for my applications and my user experience to be good, my data has to be near my compute, or at least close to it, maybe in a campus environment. And if the data isn't, of course, then I have to move that information around. Until now. Now, if you look at some of the traditional approaches to solve this problem, it's a couple things. One, let's try some WAN optimization. And that's fundamentally ways to compress or dedupe the data, to do some interesting things to the transport itself, but fundamentally, you're still moving information around. The other approach, kind of new technology, is let's talk about caching. And there's a lot of companies that rely on caching technologies, and there's some intelligence behind that. Well, I'll try to pick and choose the data that I need to move ahead of time so that when you get to that, let's say the office in the morning, my data's there. And it's still fundamentally moving copies around. And if I chose incorrectly, or my data changes too frequently, or it's too large to move in time, then that technology falls apart as well. A different approach is really this better way, which is if I want to use and execute and literally reach remote data and use it in place, that's what we're going to talk about. Just leave it and access it. But if I still want to move or migrate or back up that data, let's move it faster and let's move it with less risk than ever before. And I'm not just talking about the security of data in flight, but the risk associated with not getting the information you need in the spot where you need it the most. Now, the only way this can work is if we can make this long distance, high latent WAN actually perform like a global local area network. Now, if we can do that, this is really the utopia of what we've created. It's real-time access across a distributed elastic enterprise. The idea behind this is you pick the compute of choice. Maybe it's the cloud, maybe it's prem, maybe it's edge compute, maybe it's in a co-location. And you allow that compute to reach across this geographically distributed environment and work on data in real time wherever that data is created. The idea is to glue all this together so that you do get things like real-time access. And I'm doing it on a geographically distributed enterprise. But I also want to make sure that I have that elasticity, that I have the agility to bring data sources in and out, data compute in and out, and applications. This is what fundamentally we've created with exploiting this RDMA. Now, the best way for me to show this to you is to show a demonstration, and then we'll talk about how we actually do this. Now, to do a demo, one of the easiest ways to show this is to show a comparison. So what I've done is I've chosen the compute in the cloud. In this case, it's AWS on the West Coast, and I have two instances that are running there. One is going to be doing things using the vicinity method. The other is the more traditional approach. So that's where my compute and that's where my applications reside. My data, however, is on the East Coast, roughly separated from my compute and my applications by almost 3,000 miles. Now, what we haven't done is taken a copy of the data and pre-positioned it, pre-cached it, moved it anywhere close to the West Coast compute in any way, shape, or form. Now, what you're going to see here is we're running the exact same compute, the exact same instances, running over the exact same network, hitting the same data. The only difference is that on the vicinity method, we're going to be tunneling through a virtual machine on the way in and out of the cloud, and we have another virtual machine sitting by the data. So it's a bookend approach. Other than that, it's the exact same environment. So what I'm going to bring up here are a couple windows. Now, this blue window, this is the vicinity method. And the way the technology presents itself is through standard files and folders and shares. So as long as your applications can work with what you see here, then there's no changes to the application. And what you see is actually the pointers or the metadata of the physical data that's still on the East Coast. Now, I also have the more traditional approach. So these are the two instances that are running in AWS on the West Coast. And we're going to do a couple things. First, we're actually going to just move a file. And again, if you want to migrate, backup, move information from A to B to standard table stakes, this is what we're going to show you. We're going to show how we can create this global local area network. So what I'm going to do is I'm going to take this 5 gig file here. This is just random numbers. I'm going to drag it from the East Coast into the West Coast in the cloud. And you can see here we're running about 5 or 6 megabytes a second. Now, if I do the exact same thing on the Vicinity instance, same file, same network, same data, take this file, we'll drag it from the East Coast up into the cloud on the West Coast, and instead of 5 or 6, what you're seeing is 155 plus. And I'm able to sustain that throughput over distance, and that's important. So yes, it's faster, but what we have is a carve out, and we're getting about 95% of the utilization for the bandwidth that's afforded to this particular demonstration. And if I can run networks at 95 plus percent, that's essentially a local area network, but I'm doing it using the global wide area network. Now let's see what we can do from an application perspective. So I'm going to show you two. So the first one, this is a 3D modeling application, and this one's specific to seismic survey data. The idea is that a boat goes out in the ocean floor, does a sensor sweep, they come back, and they decide if there's oil there or not. But you can see how this could apply to AutoCAD, it could apply to any kind of 3D modeling. In fact, any application where I need to use remote data over distance. And the way this works is it works very similar to AutoCAD, and I'm just going to bring in some layers. So I'm going to start on the traditional side. Now remember, this application and the compute associated with it are running in Amazon on the West Coast, but the data is still on the East Coast. So I'm going to start here on the traditional side, and we're just going to add in a horizon. We'll do the same thing over here on the vicinity side. Now at this point, up comes the options that I have to work with. We're going to go ahead and select all the options. Do that on the traditional first. We'll come over here to the vicinity method, and you can see the checks come up. I hit OK. Now at this point, I am literally doing 3D rendering on data that's 3,000 miles away from my application. But the beauty behind this is that I'm getting the same user experience as if I had already taken the time penalty and associated storage costs and so forth and moved the data beside the compute and the applications, but I haven't. And over here, you can see what we would expect without Vicinity, which is I'm sitting around waiting. This is why you fundamentally had to move data around because of this type of interaction. Now I want to show you something else. So let's do something with video. So what I have here, this is Adobe Premiere, and we have some content that was given to us a while back. This is an interview with some baseball players. What I'm going to do is I'm just going to play the data. So I'm going to take this interview and I'm going to drag it into the window here in Premiere. And what we've done is we've turned on something called dog ears. And you can see it here, hopefully in the middle. You see total and dropped. That represents the frame count. So I can keep track of how many frames I'm supposed to get and how many I didn't. Now, if I play this, give it a second to start here, and what you're going to see is the total count go up. There we go. And then what you're also seeing is it's dropping frames and the user experience, the video is jittery, it's jerky, the audio's off, you're pausing, you're waiting. If I had to do anything with this as a analyst or a media and entertainment person here, this would be a horrible experience. Now, if I do the same thing on the Vcinity side, I take the exact same file, the exact same network, same instance type, same application, we drag it over here into the window, and you can see the dog ears associated. I'm going to hit play, and you can see that we're not dropping any frames. And what this allows me to do is really leverage this RDMA architecture to work with data or content that's thousands of miles away. So how do we actually do this? So let's go back to the PowerPoint here. Okay, now there's not one particular thing. Yes, it exploits RDMA, but you have to do some other things associated with that. And it's this marriage of a lot of things put together in a very unique way that allows this speed and sustainment of throughput over distance so that I can migrate or back up data faster or work on data in place without having to do that. And it's all done without compression or dedupe. This is done without manipulation of the data. So let's talk about how we've done this. First, let's talk about the fabric. So yes, we're using RDMA. It's essentially a mechanism, if you think about things like InfiniBand or Rocky fabrics from the high performance computing industry. And RDMA is the fundamental mechanism for creating that fabric. The problem had always been that if you try to take RDMA and stretch it or extend it at global distances, it doesn't work. Well, we figured out how to do that. There's a lot of patents around this technology, but fundamentally what we're doing is we're leveraging RDMA to move data over distance. Now, what does that mean? So one thing that we're not using is TCP. It's great for the local data center, but it's very chatty. And if you do that over a long distance, high latent WAN connection, you're going to get horrible performance. So some people have tried to use UDP, which helps a little bit. And what you can see is there's a little bit more data and less overhead. But fundamentally, what you're doing is you're throwing the data on the wire and then you're hoping that it gets there. And what that means is you've moved the problem of did it get there to somebody else to take care of. So it helps a little bit, but there's still some fundamental problems. Now, if you take a look at the top bar here, this is what we've done with RDMA. Fundamentally, what we're doing is we're moving more bits of data and less bits of overhead. And if you want to see this in graph form, it's very similar to what you saw in the demo. This is it right here. If you look at a traditional approach where you have distance or latency on the bottom of the graph on the horizontal, and you have performance or throughput on the vertical, you can see that very, very shortly in terms of distance, my performance really goes south. And if you compare that to what we've done with RDMA on this graph, you can see how the performance is sustained regardless of really the distance associated with it or the latency. And that's fundamentally what you saw in the demo. Now, in terms of just using RDMA, there's some other things you have to accomplish. Let's talk about that. So one of them is we want to make sure that we're not putting data on the wire unless the receiving end has specifically said, now I'm ready to receive it. It's very similar to fiber channel and storage area networking, kind of the buffer crediting mechanism. It's a variant of that where I'm not going to put data on the wire unless the receiving end has specifically said, okay, now I'm ready to receive data. And oh, by the way, you can send this much. That guarantees us that lossless or deterministic approach to moving information. The other thing that happens, since we're not using TCP, is sometimes people question and they say, well, what happens if you lose information? TCP is very good at error recovery, at least on a local area network. So we've done something very similar. The idea is that it's up to the responsibility of the Vcinity products, and you saw that as two VMs, one in the cloud, one local to the data, it's their responsibility to keep track of information and did it get there or did it not? So for example, let's say 100 packets got sent and on the other side, only 99 of them were received. Well, normally what would happen in a TCP environment is you would go back to the initiator and say, please retransmit everything that was in that window. And oh, by the way, all the data that was in flight, you lost. It's very disruptive. Our approach is a little bit different. meaning that if I miss that one packet at the receiving end, I'll hold the other 99 in buffer, go back to the vicinity initiator, not the computer or the application, but the actual vicinity product, and say, please selectively resend that one packet, maybe packet number 12, that was missing. We'll resend that one packet, put it back in order, and release it to the end site. And that's a very efficient and a very effective way, a very fast mechanism to do error recovery. And the beauty behind that is to the actual initiating application or computer or to the target at the other side, they never saw a retransmission request. It's kind of cleaned up the environment for them. And oh, by the way, the other piece though is we have the intelligence built in to only move what the application is asking for at any given time. A lot of times people ask two very important questions. So you're not moving the entire data set, but you have to move something. So what are you moving? Well, we're only moving what the application needs. And the second question that might come up in your mind right now is, well, how do you get around latency? I understand you're using RDMA. It's very lightweight, very efficient, very low latency, and you figured out a way to keep it alive on a global scale. And you're only moving the pieces of interest, but how do you get around latency? Well, let's refer back to the demo. What you saw is that we can sustain throughput 90, 95 plus percent over distance on a global scale, very similar to a local area network. And we see a lot of cases where, I can fill up a pipe with data, but thousands of miles away, I'm not getting the same performance of what I put in. It's just kind of dribbling out the other side. That changes. I always use an example of a garden hose. Let's say there's no water in a garden hose, maybe a 100-foot garden hose. If I turn the water on the source, it takes a little bit of time for that first drip of water to get to the other end. But as long as the thing is turned on full, then I will get all of the data, all of the water right after the first drip. We do something very similar. So yes, we're only moving that one little piece. And oh, by the way, that one little piece, the very first bit of that will always incur the physical latency of the link. That's physics. We can't get around that. But the second and the third and the fourth bit come right after the first with the performance of a local area network. So what we've done is we didn't remove latency, we minimized the effect of it after the first bit. And the beauty behind that is most applications can tolerate that. So it takes me an extra 70 milliseconds to start that video that you saw, or it takes me an extra 70 milliseconds, and I'm using that because that was a latency on the demo, of the 3D modeling tool to run. That's pretty much irrelevant. Now, there are some applications, usually around deep learning, where I need everything in memory, the entire data set, in order for my application to run. In that case, let's go back to the first side of the coin, which is, I can sustain throughput and we'll move the data faster using this RDMA thing than ever before. So if you need all the data, get it faster. If you don't need all the data, just move what's appropriate, use it, keep it in place. Now, one of the other things that we've done is you want to make sure that it integrates with tools so that the application can use the data with protocols that it already understands. Things like NFS or SMB and SITs or even object at S3. We want to make sure that those local vicinity things are presenting into their respective environments in a mechanism that you don't have to change the architecture or the applications to use. Like you saw in the demo, we just want it to look like standard files and folders and shares, and that's what we've done. So to the end stations, to the storage, it's an NFS export that we can present logically out to remote locations. To the clients at either end, all these remote sites, it just looks like a network folder. The idea is to make it simple and easy so that the processes, the workflows, and the applications can use it in the way that they're comfortable with and something they already understand without having to put software and training associated with other things to make it go. In the middle, we'll change it and use that RDMA thing. Now, one thing that I didn't mention is that RDMA protocol that we use, we wrap in an IP header. And the beauty behind that is it can run on any IP associated network. It could be the internet, dedicated links, 5G, Wi-Fi, satellite. It's transport agnostic. So our idea is we're trying not to change a lot of things, but incorporate it into the mechanisms and the architectures that are already out there. Now, in terms of the logical high-level piece, this is really what it looks like. Again, the idea is that it is a bookend approach, although one can talk to many. And you only need one vicinity element. Could be either a piece of software or some hardware assist, but the idea is you need only one in your environment because it looks like a storage device. It's not an inline piece. You just put it in the architecture, take this VM, put it on a server, put it in the architecture somewhere, people point to it. You don't need one for every user, you need one for each location. And then you can set up a construct which allows you to bring in maybe cloud, colo, compute, edge, and you blend it all together, right? But the idea is there's no software to install on the clients, there's no application changes, except for file open, you point to a different folder, and that folder, as you saw in the demo, when you bring it up, it looks like the data's there, it's the metadata, it's the pointers of the physical data that's somewhere else. When you go to use it, we'll reach out over distance using RDMA, bring that back with all the flow control and stuff that we talked about to give you that local performance. And we essentially reverse it back on the other side. And again, this isn't about compression or dedupe. It's not about manipulating the data. It's about manipulating or changing the mechanisms of transport and leveraging existing technologies and open source pieces so people can use it in a way they understand. Now, we talked a little bit about security in the beginning. One of the other things that this does is it allows you to encrypt data in flight. Standard AES-256 and some other algorithms we've baked in here. But we've also added obfuscation. And the idea behind this is if I have multiple WAN transports at my disposal to use, well, then we can take the flow of data and we can carve it up and stripe it or spray it across these paths and put unique encryption keys on them. And the idea behind this is, yes, I can encrypt the data, but in this case, you see three paths. And if anybody got hold of a path and its associated key, in this case, they only got a third of the data. So it's a nice way to enhance standard in-flight encryption with obfuscation. Now, what does this really mean for you? The idea behind it is there's a couple things that are unique and give you options in the way that you want to use or connect your enterprise over distance. One of the first and primary things to take a look at is cloud. Everybody wants to move to the cloud. The cloud has a lot to offer. There's a great elastic compute in the cloud. But in some cases, people can't move the data to the cloud. There could be a lot of reasons. My data changes too frequently. The data is too large. I have compliance or regulatory reasons. Well, now you have an option to use the compute in the cloud, just like you saw in the demo, against data on-prem or data at an edge. So let's, really augment the cloud compute technology. The other thing that people don't realize is a lot of companies have this mandate to move things to the cloud, right? It used to be cloud first, now I think it's cloud appropriate. But what is appropriate? The only way to really tell is to take your applications and the data traditionally and move both into the cloud. And that takes time and resources and storage costs associated with that. Well, now think about this. You have a way to use the compute in the cloud, just fire up the application, but don't move the data. Keep the data on-prem. Now I have a risk-free, very fast mechanism to see if it makes sense for applications to perform in the cloud without having to take the time penalty and the risk of moving the data as well. And the other piece, and you saw this on the demo, if I just need to migrate data into the cloud, let alone applications, or between data centers, now I have a fast mechanism to do that. The other piece, though, is let's talk about edge. Well, I have some unique things going on. We call this removing the stranded or stale edges. One of the beauties behind edge compute now is the ability to curate data. I want to normalize my information. Maybe I want to run compute in the cloud. I want to run my AI machine learning algorithms against edge data. But I don't want to look at one edge source. I'm going to look at various disparate data types, maybe everything from social media to weather to financial algorithms. The whole idea is I want to do data fusion. Well, normally what would happen is you would do some compute at the edge, but then you had to transfer that data to the cloud or to another data center in order to monetize that, to use it. And at the time you're waiting for that transfer to occur, your data is becoming stale or isolated. Well, think about this. That all goes away. Now I have real-time access to the edge, meaning I can curate my data and the cloud can immediately leverage that and monetize that. And what you really have is geo-distributed AI with compute in the cloud against data at the edge or any combination of colo or data centers. It's a whole different approach to real-time data fusion. If you have any more questions or you would like some more information on the way that we've leveraged RDMA and a lot of the other things that we talked about in this little scenario here and a demonstration, please reach out to us at Vcinity.io. And also, please don't forget to take a moment and rate this session. Thank you very much.